Okay, so the main topic for this week is summarizing bivariant data. So we went over creating these scatter plots. Now, what do we do with the data once we've put them in those scatter plots? So for example, let's say we found the age and weight for each person in a sample of 10 adults. Is there a relationship between the age and the weight of these adults? So our table here shows their age and the weight for each of the people that we selected. Do you think there's a relationship? If so, what kind? If not, why not? Obviously, at young ages, there's a relationship because people grow when they're young. As they get older, they get larger. But as they get above that certain age, that growth age, does that continue to be true? And that's what we're going to explore here in this example. So first, we're going to create a scatter plot. So we put the age along the bottom axis down here and the weight along the side. So this one here is the youngest and also one of the lightest people in our study. Up here, however, this is one of the oldest and the lightest person. There does not really appear to be a relationship between the age and the weights among these adults. These appear to be scattered all over the graph. So in this same situation, oops, got kicked back a notch here. So we find the height and the weight for each person of these 10 adults. Rather than the age versus the weight, now we're looking at the height versus the weight for these adults. And we're going to create that scatter plot. Now the height goes across the bottom rather than the age, and the weight goes up the side. Now as we look at this, there definitely appears to be a pattern. It's positive because as we go across the graph, right to left, it's going up. And it's relatively strong. I mean, they're fairly close to that line. When we ask strong or weak, weak would mean, yeah, they kind of follow that pattern, but they're all way off the line. Strong would mean, yeah, they're pretty close to it. My line is kind of choppy there. Something like that would be a little bit closer to all of them. So when we look at correlation, what makes the correlation positive or negative, and what makes it weak or strong? And what does it mean if the relationship is positive or negative? What does it mean to be weak or strong? What would that look like on the graph? So here, this is a positive relationship because as we go left to right, again, the values go up. That's positive. It shows a strong relationship because I could draw a line through those points, and all those points would be relatively close to that line. So our strength is how close the points are to the line. Weakness would be they're further away, strong means they're closer to it. Positive means that line has a positive slope. Doesn't necessarily mean that it's how positive it is, just as long as it's positive, period. This set, however, has a very weak relationship, and you really can't tell if it's positive or negative, maybe slightly negative, but really you can't draw a line through them at all. So there's very little, very, very weak or no relationship at all there. This one here has a weak relationship because there does seem to be a downward trend. You could put a downward line through there, a negative sloped line. So I'd say it's a negative relationship, but they're weak because those points are not really close to the line. They're farther off the line. This one here, you might want to call it a positive linear relationship, but it is really not quite linear. There's definitely a curve to it. So it's actually not a bad relationship. It's a relatively strong relationship, but it's not linear. It's curved. So we have to identify, first of all, as having a positive or negative relationship or no relationship, and then the strength of that relationship. Heights of mothers and heights of their adult daughters. That should be a positive relationship. The taller the parent is, the taller the child should be. Age of your car in years and its current value. That should be a negative relationship. Older the car gets, the less it's worth. Weight of a person in calories consumed. Assuming that calorie consumption has been consistent over time, that should be positive. Height of a person in the person's birth month. There should be zero relationship there. month you're born should not have a correlation to your height. Number of hours spent in safety training and the number of accidents that occur. This should be a negative relationship. The more safety training you have, the less accidents you should have. So to summarize, the value that summarizes this relationship is called the correlation coefficient. And it's represented by a small r. It's a quantity that basically assesses the strength and the direction, so positive or negative, of a linear relationship in this bivariant data. There's something called the Pearson sample correlation. This is what we use the most. Population correlation coefficient, rho. And then there's a statistical correlation coefficient. The equation for R is 1 over n minus 1, where n is the number of pairs, the number of ordered pairs in the data, times the sum of, for each data point, you take the x value minus the mean of all the x values, divided by the standard deviation of the x values, times the y value minus the mean of all the y values, divided by the standard deviation of the y value. Those values, by the way, are called the z-scores for every value, every x value of each coordinate and the y value of each coordinate. You are combining those together. So for the 6 primary undergraduate universities in California with enrollments between 10,000 and 20,000, 6-year graduation rates, that means 6 years after the start of college, they have graduated. And student-related expenditures for full-time students for 2000 were reported as follows. So the expenditures, the amount they spent, and their graduation rate. So there's our graph. Now, these are pretty scattered. Doesn't really appear to be much of a relationship, so we're expecting a correlation coefficient to be really low. R 0.05 is pretty small. Closer to 0 is a very weak relationship. Closer to 1 or -1 would be a very strong relationship. In order to interpret what this number tells us, we investigate the properties of the correlation coefficient. So the properties of our correlation coefficient, legitimate values that correlation coefficient R will always be between -1 and +1, where 0 is no correlation at all. Between 0 and 0.5 in either direction is a weak correlation. Between 0.5 and 0.8 is moderate, and from 0.8 to -1 or 0.8 to -0.8 to -1 and +0.8 to +1, those are strong correlations. Now, these numbers depend on how many points are in the data set too. If you have only 8 or 9 data points in your data set, this is probably what these values are most descriptive of. If you have 50 or 60 ordered pairs, getting a correlation coefficient of 0.7 is actually a pretty strong correlation. So what we've given here is really only valid for data sets with that 8 to 15 ordered pairs. Suppose the graduation rates were changed from percents to decimals. We divided them by 100. Transform the graduation rates and calculate R. Well, when we graph them, we get all it does to the graph is it kind of squishes it down vertically. Our R value is exactly the same because we didn't change the data at all. All we did was altered how we represented it a little bit. We divided everything by 100, which all that would do is take the slope of any potential line that described them and divide it by 100. Really, there isn't a line that describes these, so it doesn't matter. Now, if we do the following transformations and then calculate R. So we're going to do each x value. We're going to add 14 to it and then multiply by 5. Each y value, we're going to add 30 to it and divide by 4. Well, we still have the same correlation coefficient. The reason is what we performed here is a linear transformation. Both of them were. We didn't, do square anything or square root anything. So they're linear. These, if I multiply this out, this is a linear equation. That's just 5x plus 70. This is a linear equation. This would be 1/4 y plus 7.5. They're both linear equations. So it's linear transformations. And linear transformations do not change the correlation coefficient, whether applied to one or both variables. Suppose we want to estimate the expenditures per student for given graduation rates. Well, because all we're doing is switching the variables, the correlation coefficient is still the same. Not depend on which variable is considered dependent or independent. So now suppose the 33.9 was really 63.9. So we're just going to change that one value. What does that do to the correlation coefficient? Well, this will significantly change it. We revise our plot here. That was a 33.9 has gone up to 63.9. Now you might be able to argue that there's a positive relationship. Notice that point moving up, from down here moving up, has drastically changed. It went from a 0.05 correlation to now a 0.42. That's now a moderate relationship. Well, not quite moderate, but just in the upper end of the weak relationships. The extreme values drastically affect the correlation coefficient. So the value of R is affected by those extreme values. So let's compute a correlation coefficient. So I have these ordered pairs here. I got the ordered pair negative 340, negative 120, 18, and on down the line. If we compute it, R equals 0. What that means is there's no relationship between these points. We sketch the scatter plot. Actually, what we see here, this is actually a parabolic relationship, quadratic relationship. But there is no, the R equals 0 means there's no linear relationship. Not that there's no relationship at all, but it's no relationship that can be described by a line. So there is a definitive shape, it's just not a line. So R is the measure at which the data can be described by a linear relationship. The properties of R. Legitimate values of R are -1 to +1. Not changed by any sort of linear transformations. Does not depend on which variable is the X or Y. The correlation coefficient is affected by extreme values. And it only measures linear relationships, not nonlinear relationships. So back to this example. In order to interpret R, recall the definition of the correlation coefficient. A quantitative assessment of the strength and direction of the linear relationship between bivariant quantitative data. Well, that's being very close to 0 would say that there's a very weak or really no relationship. This says weak positive linear. That small, I wouldn't call it a positive relationship. I would just say there is really no relationship there. Does a value of R close to 1 or -1 mean that a change in one variable causes the change in the other? Now, this is a good thing, a big thing. Causation is not implied by a correlation coefficient. Just because there's a strong correlation between the two variables does not mean that one causes the other. There could be a third variable out there that causes both of them to change. So consider the following examples. The relationship between the number of cavities in a child's teeth and the size of his or her vocabulary is a strong positive relationship. Does this mean that increasing the vocabulary changes their teeth? No, of course not. Both variables are strongly related to the age of the child. As the child gets older, they're going to have more cavities and stronger vocabulary. Consumption of hot chocolate is negatively correlated with crime rates. Should we all drink more hot chocolate to lower crime? Well, of course not. Cold weather triggers more hot chocolate consumption. Cold weather also tends to lower crime rates. So causality can only be shown by carefully controlling values of all the variables and that might be related to these variables. So in other words, we would have to eliminate those changes in any other variables other than the two we're looking at. Those are what we call confounding variables. Unless we can control those, we cannot assume any sort of causality. The correlation does not imply causality. And they're going to repeat that a few times. That is a common misconception. Correlation does not cause or does not imply causality. So what is the objective of a regression analysis? It is to supply a relationship between those variables. So let's say we have X is the amount spent on advertising and Y is the amount of sales for a product during a given period. Well, knowing the relationship between these variables might help us plan our budgeting process. The objective of regression analysis is to use information about one variable, and usually X, to draw some sort of conclusion about another variable, usually Y. So the X variable is the independent variable, or it's called the explanatory variable. It's the one that we're manipulating or we're allowing to change. The Y variable is the dependent variable, the response variable. It is the one that's responding to our changes in the X variable. Its values depend on what the values of the X variable are, if there's a relationship. So we will use values of X to predict the values of Y. That's the goal of the regression process. So we create a scatter plot to exhibit a linear pattern. When this is the case, it makes sense to summarize the relationship between the variables by finding a line that is as close as possible to those points. And there's several processes to find a line of best fit. We're going to use least squares regression line. The form of that line is y equals a plus bx. Some call it y equals ax plus b. It's the same thing. It's just saying that there is a y variable is equal to some sort of y-intercept plus a slope times x. Y hat is just the predicted value of y. Make sure you put the hat on that y because it is the predicted value, not always the actual value. B is the slope of that line, as we said. It's how much, for every increase in the x variable, it's how much the y variable will approximately increase. And A is the y-intercept. So that's the value it would take on if x was 0. So in some situations, the y-intercept is kind of meaningless because, if you're looking at age versus weight and stuff like that for kids, I should say that weight versus calorie requirements for children. There is no 0 weight, so that y-intercept is not significant because there is no real data point for a person who weighs 0 pounds, so their calorie requirements is kind of nonsense. So the slope of the least squares regression line is the sum of each x value minus the mean of the x values times each y value minus the mean of the y values divided by the sum of the x values minus the mean of the x values squared. The intercept is found by just taking the average y value and the average x value and substituting them into this equation. So the LS, the least squares regression line, is the line that minimizes the number of the squared deviations from norm. Let's explore what that means. So let's say we have data that consists of those 3 points. Well, they're obviously not in a line. Want to just fit a line to the data by drawing a line through what appears to be the middle of the points? We can try that. That line there, not really close to any of the data points. It has an equation of y equals 0.5x plus 4. We can find the vertical distance to each point. So y hat is the predicted point for 0. This is x equals 0. That would be -4. So the predicted value here would be -4. The actual value is 0. Sorry, it's -4 is the difference between the value and the predicted value, I should say. For 3, 0.5 times 3 plus 4 is 5.5. Compare that to the 10, that's a difference of 4.5. Put in the 6 Well, 0.5 times 6 plus 4 is 7. Compare that to the 2 here. That's a difference of 5, so it's a negative 5. Those are, by the way, what we refer to as residuals. Those are the deviations, so we square those and add them together would be the sum of the square deviations. So negative 4 squared is 16, 4.5 squared is 20.25, and negative 5 squared is 25. That adds up to 61.25. That is the sum of the square deviations, or the sum of the squares. Can we draw a line that has fewer? Well, this one here, y equals 1/3 x plus 3. We could go through that whole process, finding those deviations, each of the points, and we square those, we get a smaller number. So that's a better line because the sum of the squares are smaller for that line. So rather than just trying new lines over and over again and seeing which one gives us the smallest sum of squares, we go through that process to calculate that least squares line. So given this data here, we're studying the pomegranate's antioxidant properties to see if it might be helpful in the treatment of cancer. In one study, mice were injected with cancer cells and randomly assigned to one of 3 groups. Plain water, water supplemented with 0.1% pomegranate fruit extract, and water supplemented with 0.2% pomegranate fruit extract. The average tumor volume for mice in each group was recorded for several points in time. X equals the number of days after injection of cancer cells in mice assigned to plain water, and Y the average tumor volume in millimeters cubed. So Y is the number of days, X is the size of the tumor. We get that graph that sure looks like a linear relationship to me. So let's calculate the correlation coefficient. Now remember what the correlation coefficient looks like. And our regression line. So remember that correlation coefficient is positive, which means that this is a positive relationship. As time goes on, the tumor gets larger. It's close to 1, which means it's a very strong positive relationship. This over here, this is the y-intercept saying that at day 0, the tumor was negative 269.75 millimeters in size. And each day it tended to gain 37.25 millimeters. Now remember, they didn't start collecting data until 150 days after the cells were injected into the mouse. It takes several days for the cells to actually latch on and start to grow. So there was 0 growth during those first several days. So this negative y-intercept is meaningless. The cells were never a negative size, but there was several days at the beginning where there was no growth. So really this regression line starts at a point where the cells start to grow, but we just don't know what point that was. So we interpret the slope and the correlation coefficient. The slope, 37.25, means that, yeah, every day we'd expect that to grow by 37.25 millimeters. And then, of course, this is a very strong positive relationship. So the average tumor volume and the number of days since injection tends to be very positively, strongly positively related. The intercept really doesn't have any meaning because there's at no time were the cells negative in size. So now we can use this regression line, since it was strong, we can use it to predict the volume of the average tumor for 20 days after injection. Well, if we do that, we come up with 475.25 millimeters cubed. That would be our prediction for 20 days. If we predict for 5 days after injection, however, we get a negative number. What that's telling us is the linear relationship doesn't start until after 5 days in. That really doesn't make sense. The volume can't be negative. So if we get down too small, this regression relationship, this equation doesn't work. The data in this case went from 150 days to whatever. We want to stay within the range of the data. If we get too far, we know that the relationship is linear within that data range, but outside of the data range, it may not be linear anymore. So it's not known whether the pattern continues outside of the range of that data. Suppose we want to know how many days after injection the cancer cells would average 500 millimeters cubed. We put that in for y now. We solve. Oops. If we tried to put it in for y hat and solve, would that be appropriate? Well, the slope should be just an inverse, but unfortunately, the y-intercept that we'd use would not correspond to the value if we just put in 0 for y hat. So it is not usually appropriate to try to predict backwards, where we choose values for y. We try to calculate what value for x would have given that. Generally not a good use of our regression equations. So the regression line of y on x should not be used to predict x because it is not what it is for. The regression line is used, the one that we have here, this one right here, this is used to predict y from values of x. The hat says that y is the variable being predicted, not x. So we can't use y to predict x here. This is using x to predict y. This is a totally separate equation. This is using, the hat says x is the variable being predicted from a value of y. It's a totally separate equation. So let's, looking at these, this value here, let's find the mean of the x values and the mean of the y values. X bar is 19. If we add these up and divide by 5, we get 19. Y bar is 438. We add these up and divide by 5, we get 438. Plot the points of averages on the scatter plot. So here's our scatter plot right here. The point of averages is x equals 19, y equals 438. Will that always be on the regression line? Yes, it will, because we use the formulas to find the slope, but remember, we use that x bar and y bar to find the intercept. So our intercept was determined based on this point being on that line. So let's investigate how this least squares regression line and the correlation coefficient change when different points are added to the data set. So here we have a simple data set. We're going to sketch our scatter plot here, calculate our y, our regression equation, and our correlation coefficient. We're going to move that off to the side now, and we're going to change. We're going to add 1 point to it. We had the 0.58. So we put that point on our graph here. That's an outlier. It's away from the other points. Notice how it drastically changes our equation. And of course, the correlation coefficient. 12, 12. That one's actually really close to the line. When we add that, notice it does not change. It changes our regression equation a little bit, but it does not change our correlation coefficient much. It does not have drastic changes based on that point being added to our data set because it was close line. It was not an outlier. 12, 0 is going to be a point way down here. Now that's an extreme outlier. Notice it totally changes the tone of our equation. Actually get a negative slope instead of a positive slope. So remember, both the correlation coefficient and the least squares regression line are extremely affected by those outliers, those extreme values. So for this, the pomegranate, remember, we can look at Minitab and do the data output. We do the regression equation to predict the volume. It'll give us that equation and these constants. Notice there's our y-intercept and there's our slope. P-value, that is telling us whether, if we do a t-test for whether this equation is strong or not, that's telling us, the p-value is telling us this is a pretty strong regression equation. Now, it's not giving us the actual correlation coefficient here, but the p-value is telling us that this is a strong relationship. That's basically saying what's the percentage that this was caused by random chance, and it's that small percent means no, it's not a random chance. It's generally a strong relationship. So we got our intercept, our constant, and then our days is the slope. The rest of that will be discussed in chapter 13. So once our least squares regression line is obtained, the next step is to examine how effectively the line summarizes the relationship between x and y. Important questions are, is the line an appropriate way to summarize? Is it really appropriate to use it, or are there other measures that would be a better estimate? Are there any unusual aspects of the data that we need to consider before we can use that line to make predictions? And if we decide to use the line as a basis for prediction, how accurate can we expect those predictions to be? So we look at the graphical and numerical methods to answer. So here's a data set on the distance a deer mouse will travel for food from the food to the nearest pile of fine wooded debris. So many tabs used to make this equation here. So this is our intercept, that's our slope. So this would be y equals 3.234x minus 7.69. Make sure I put a hat over that y because that y is being predicted. And there's our equation. They did it backwards from what I did, but this same equation. So let's plot our data and the regression line. So there's our data and our regression line. Now the points look like they're reasonably close to it, but they're not dead on, that's for sure. The vertical distance from each point to our regression line is called a residual. That measures its distance from the predicted value to the observed value for each data point. We did this before when we looked at the definition of least squares. This one's above, so it's a positive residual. This point's below, so it is a negative residual. So each residual is the predicted value subtracted from the observed or actual value. So we get that predicted value for each data point using our regression equation, and we subtract the actual value minus the predicted value. And we see these are the residuals. The sum of the residuals should equal 0 or really close to it. If we square them, that's why we have to use the least squares, because when we add these up, positives and negatives should cancel out and get 0 for us. That's saying that we're equally above and below the line. So that's why we square them to get the least squares. Very similar to our step in calculating standard deviation. So residual plots is just a scatter plot where we plot the x value, but rather than plotting the y value, we plot the corresponding residual that goes with it. When we look at these residual plots, we're looking for no pattern. If there is a pattern in the residual plot, that is telling us that then the linear regression is not valid, that there's a predictable pattern in the residuals, means that it was not a linear regression. There's probably some other shape that was better to predict. So here there's no pattern. So we'd say that that was a linear model is appropriate. Here, however, there does appear to be a pattern. So we might say that there might be a better model than a linear model to use for this. We're saying in the smaller values, it's large residuals, and the higher values, it's large residuals. In the middle, it's right on the line. So our linear model is probably not the best model for that. So looking back at the deer mouse going for food, we look at those residuals. If we plot these against the distance, of course, that's our distance from the debris is our x values. This is going to be our y value on our residual plot. We see there really is no pattern. You'd have to really stretch to find a pattern here. So a linear model is most likely appropriate here. So since now the plot of residuals against the predicted distance for food, so that means that we can use our regression equation. So what do you notice about the general scatter of points on this residual plot versus the residual plot using the x values? So now we're, instead of doing the predicted travel distance, instead of doing the distance from the debris, we're doing the predicted travel distance. You can see there's similar shape to that residual plot. So we can actually do residual values on either be plotted against the x or the y values. We prefer to do them against the y's. So let's examine the following data set. The following data is for 12 black bears from the boreal forest, where x is their age and y is their weight. That's the scatter plot. So there's a scatter plot. Very few bears make it past about 12 years old, so that's why it's so clustered together there. And you can see they do tend to get a little bit heavier as they get older, but it doesn't look like a great relationship. If we took this one outlier out here, it would really drastically change this to look like that. Do you notice anything unusual about the data? Again, we mentioned that outlier. That outlier is going to totally change our regression. We really need to remove it from the data set to make this a valid regression, or just say that we can't do a valid regression. So remove that data point. Notice that line takes on a totally different shape. So that's considered an influential point because it affects the placement of the line drastically. Notice that this observation has the largest residual. It's the furthest away from the line going vertically. Even though this one is right there, it's right on the line, it's still an extreme value because it's way away from the other data points. An observation is an outlier if it has a large residual. So it's really not an outlier, it's an influential point. So I should be careful on how I say that. I said that was an outlier. It isn't. It's an influential point because it's way away from the others. It has a drastic effect on the results if we leave it in the data set or if we remove it. But it's not an outlier. An outlier is the distance from the line. The next thing is something called the coefficient determination, which is strongly linked to our correlation coefficient. In fact, it's r squared. It is the square of the correlation coefficient. It represents the proportion or percent of the variation in y that can be predicted or attributed to the approximate linear relationship between x and y. So it's the amount of the change, the variation in the variable y that can be predicted through this relationship. So here is the distance to the food pile and the distance the deer mouse will travel for food again. Suppose you didn't know any x values, what distance would the deer mouse you expect the deer mice to travel? So those are all of our y values here. If we didn't know anything about the x values, the mean of the y values would be 15.938. If we drew in a line that was just the mean of the y values, that is sometimes used as a predictor. We find those residuals there using the square of the residuals. So that's our square deviations again. SS stands for the sum of the squares again. So this is the sum of our squared residuals. We square them because if we don't, they're going to add up to 0. Total amount of variation in the distance traveled is 773.95. If we actually use the regression equation, however, that's only 526. That's much less. So we're comparing if we don't use a regression equation, if we just use the average y value, we have residual sum of the squared residuals of 773.95. And if we know the x values and we can use that regression equation to predict, that sum of the squared residuals only goes down to 526.27. So what percent of the variation in distance traveled can be explained by the equation? We divide those two, and then we subtract it from 1. So we get 0.32, 1 minus 0.32 is about 32%. Now again, if I square rooted that, I should get my R value. Now, the R-squared adjusted is kind of interesting. It's removing data points that might be considered outliers and adjusting for those. Um, we'll talk about that at some point. Well, that would be really a discussion for a more advanced course. So let's view the values from this output and their meaning. That's our slope again. That is the y-intercept again. This is our slope. That is that coefficient of determination. So 32% of the observed variability in the distance that the mouse will travel for food is predicted by this linear relationship. What does that number represent? S. This is the standard deviation, S. It's the typical amount by which any observed value deviates from the least squares regression line. So here we have a set of data represents the age and the average marathon finish time. Let's do a scatter plot. Now, somebody in here is really young, had a very poor time. But you can see age goes on. Actually, I should say this is actually very young. It's down in the 14 or 15 range. So being younger, less conditioned, and smaller framed causes that time to be longer, most likely. But as we grow older, those times tend to increase. But you'll notice there really appears to be more of a curved relationship there. I don't know if I would describe that as linear. So since this curve resembles a parabola more than a line, we would describe it with a parabolic relationship, not a linear relationship. You can use Minitab to create that quadratic relationship. Really not part of this course. This curve minimizes the sum of the squares of the residuals, similar to the linear regression, but this is for quadratic regression. Notice the residuals from the quadratic regression still go vertical to that parabola from the regression equation. And of course, there's our residuals have no predictable pattern. R squared is still useful here to assess the fit of the quadratic regression. So we can use that R squared. Like I said, for a linear regression, R squared is we can just take that correlation coefficient and square it. But for other shapes, R squared has to be calculated independently. So this is saying that 92% of the variation in the finish time can be predicted or can be attributed to age and this regression relationship. So depending on the data set, other regression modules such as cubic, quadratic, polynomial may be more appropriate. Minitab can do these. Doing them by hand is very difficult to do. Another method for fitting regression models to nonlinear data sets is to transform the data, making it linear. So that quadratic data set maybe would do a square root to make it into a linear data set. So if there's no transformation, the equation is y equals a plus bx. If you have to take the square root, it then becomes y is equal to a plus b times the square root of x. If you do the log, well, it's log of x. Reciprocal, it's 1 over x. Log of y, of course, put the log on the y. You may also use natural log rather than the log base 10. So back to our pomegranate study, looking at these are for the mice that just use regular water. Remember, actually, we're going to use the mice to add the 0.2% pomegranate fruit extract and the size of their tumor given number of days after injection. So here's our scatter plot. There's our number of days after the injection, the size of the tumor. Let's use a transfer. Notice this is a distinct curve. That would predict either a quadratic or cubic relationship. So we are going to, it appears to be some sort of exponential growth, so we're going to try the log. When we do that, we take the log of these values. Now we graph it. It does look linear. So that does indicate it was some form of an exponential relationship. We could find that least squares regression equation. So it's telling us that the log of y is equal to that equation. So we can still use it to predict, but we're predicting is the log of y, so then to find y, we have to use an exponential, 10 to the power of, to find it. The log of y is 2.456, so y would be 10 to the power of 2.456. Another useful transformation is the power transformation. The power transformation ladder and the scatter plot below can be used to help determine what type of transformation is appropriate. So these are the names for the types of transformations. You can square the x, you can cube it, you can square root it, cube root it, and all that. Suppose the scatter plot looks like the curve labeled 1. So this curve here. That would be no transformation, would be, oops, come here, would be appropriate. What about if it looks like the curve labeled 2, that type of curve? Well, that would then probably be best to use, oops, 2 squared. If it looked like 3 here, then it would be best to use either cubic or cube root, and so on. Again, we're not going to get into a lot of those transformations in this course. But the software will do a lot of that for us. So our logistic regression, we're not going to talk about logistic regression. What it is, it's looking at if the dependent variable is categorical rather than numerical. So what we're looking for here is simply a regression equation that predicts the proportion of a certain characteristic. Okay, that is it for our data or for our material for this week. So if you have any questions on this as you're going through the homework, please let me know and I'll get back to you as soon as I can. Otherwise, y'all have a great week.